Good morning, students. So, our topic for today is the characteristics of a DC series motor. So, last class we learned what are the characteristics of DC shunt motor. So, if there is anybody who hasn't watched that video, go back and watch that video in later because all these topics comes as a continuation. So, you should understand the previous topic also. Okay, so characteristics of DC series motor, just like the DC shunt motor, there are three main cara, which is the speed armature cara, N versus IA, torque armature cara, and the speed torque cara. And you know this is the diagram of a DC series motor. We will have the DC supply will be there. Then the series winding will be in series with the armature winding. That's why we call it RC, and the current will be the armature current, the line current supply, because in the motor we supply the current, and the series current ISC, series winding resistance current ISC will also be same. So the first cara is speed armature current, that is N versus IA. So from the beginning of the our sessions, I'm telling you the equation of back EMF, because in a motor, we have the back EMF, and in a generator, you have the generator EMF. So the generator we completed in our first module, and here in the second module, it's all about motor. So it will be always what we are getting will be a back EMF. So we have the equation EB is equal to P phi NZ by 68, and you know what are all these things. So from that we can write that N is proportional to EB by phi, just like how we derived the wave, the cara in shunt motor. Here also N is equal to EB by phi, but here we know that EB, which is the back EMF, will be V minus IARA minus IARC. This expression was made clear to you when we studied the type of DC motor. So when it comes to series motor, I have explained to you how we get the equation from this. Applying a Kirchhoff voltage law KVL in this loop, you will get is V minus IARA minus ISCRC. That's it. So under normal condition, IARA and ISCRC drop is quite small and can be neglected. So we can write that N is proportional to 1 by 5. So that's why we come here, we get like speed armature torque. It will be a inversely proportional cara. This is the explanation why the cara is like this. So when the armature current increases, the speed decreases. That's the speed armature cara. And one very important concept which everybody should know is that a DC series motor, I think you might have done in the lab experiment also, like ma'am might have explained to you, like a DC series motor cannot be started on no load. Like there should be a load which is greater than 50% of the full load. At least that much load should be there for a DC motor to start. We will see why. Here, in case of a DC series motor, armature current is decided by the load. See, a DC series motor, the armature current is decided by the load. You know why. So, on light load or no load, the armature current drawn by the motor is very small. In case of a DC series motor, we know that phi is proportional to IA. On no load, as IA is small, hence flux produced is also very small. According to speed equation, N is proportional to 1 by 5, as EB is almost constant. So, here comes the point. So, on a very light load or no load condition, as flux is very small, the motor tries to run at dangerously high speed. You see the things coming? When the load is very less or at no load condition, the armature current will be very less. So in a DC series motor, armature current is proportional to the flux. So the flux is becoming very less. When the flux is very less, according to the equation N is equal to 1 by 5, the speed will be very high. That is, the motor tries to run at dangerously high speed, which may damage the motor mechanically. So that's why we say a motor should always, a DC series motor should never be started on non-load. This is a very important question. After saturation, flux phi becomes constant. Then at that case, N is proportional to V minus IARA minus IRC. As the IA increases, speed keep on decreasing up to the saturation point. After the saturation point, even if IA increases, IA, armature current, speed becomes constant. That's why after the saturation point, even if IA increases, the speed will remain constant. That's why we have it parallel to the x-axis. Constant is not changing. Okay. Speed, armature current, Kara, N versus IA. So you understood why this figure is like this. Okay. Because when the armature current increases, the flux will also increases. In that case, the speed decreases. Why? From this equation, N is equal to EB by phi. Now the second Kara is the torque armature current Kara. So here you should recollect the torque equation, the armature torque equation we derived in the previous class, which is TA is equal to 0.159 phi P Z I A by A. If there is anybody who don't know how we got this equation, please watch the previous video. Okay. So from this equation, we can write TA is proportional to phi A. But we know that up to saturation, phi is proportional to IA. Previously, we derived, from the previous concept, we understood phi is proportional to IA up to saturation. After that, it's becoming straight line, right? So we can write TA is proportional to IA square. Comparing, we can write TA is proportional to IA square. So up to saturation, phi is equal to IA. So in a torque armature current Kara, up to saturation, it will be parabolic. After that, flux becomes constant. Yes, after that, flux becomes constant means TA is just proportional to IA only, not IA square. So it will be a straight line. See, so torque armature current. So up to saturation point, this is saturation point. Up to saturation point, TA is proportional to IA. So the IA square, so it's parabolic, and after that, TA is proportional to IA. So the previous equations, everything, if you compare, you will understand how we get these equations. Because we from the previous curve, we wrote like phi is proportional to IA up to saturation point only. After saturation point, it's becoming a straight line. Flux is a constant here. Speed is a constant there. Sorry, not flux. Speed is a constant there. So here we can find like after saturation, TA is proportional to IA only. Because flux is constant after saturation. Now we have the speed torque like similar, just similar to the shunt Kara. The speed torque curve will be similar to a first Kara. The speed torque Kara will be similar to the speed armature Kara. Why? Because armature current is proportional to torque. TA is proportional to IA, so speed armature current curve and speed torque curve will be the same, and explanation is also the same. Just we have to write extra that TA is proportional to IA. That's why they are same. So all these this equation, everything you should write for this third curve also. This is a very important question in case your exam as well as your lab exam and all these things they will ask you, because these are very theoretical and very understanding questions. So here the same. Before saturation, TA is proportional to IA square, and after that flux becomes constant, so TA is proportional to IA. Now we are coming to the power equation of a DC motor. Very important concept. So here we have a shunt connected DC motor. So we have the voltage equation of a DC motor is given by V is equal to EB plus IARA. Because this is a parallel connection, the voltage here, shunt connection, V here will be equal to the voltage here. So VB plus IR is the voltage. Therefore, the back EMF EB is equal to V minus IR. This we have been deriving for many times now. So by multiplying both sides by IA, it's a derivation. So we multiplied both times by IA, because multiplying by IA means voltage multiplied into current, we will get the power. So we get the power equation as follows. EB into IA is equal to V into IA minus IA square into RA. And this is the power equation of a DC motor, where V into IA is the electrical input to the armature, because in a motor we always give the electrical input, and EB into IA is the electrical equivalent of gross mechanical power developed by armature. Because motor will develop mechanical power, but we know the significance of the back EMF in development of mechanical power. If you are not remembering, watch that video. I have already explained. So watch the video of back EMF. So electrical equivalent of gross mechanical power developed by armature is EB into IA, and IA square RA is the copper loss in the armature. So just understand how we got the equation, which are the terms. What is V into IA and what is EB into IA? Okay. Now we come to the power stages of a DC motor. So from the first class itself, I am telling, in case of a motor, the input will be electrical. So I saw just for understanding, I saw input will be voltage and current. So see, so the motor input is voltage into current. So VI, the power input, then before it reaches the power developed in the armature will have copper losses, and copper loss for the armature winding as well as the shunt winding will have copper loss. So that we should minus from that. So then we get the power developed PM is equal to EB into IA, which is also equal to 2 pi NT into NT by 60. 2 pi NTA by 60. This is all we have derived in the previous sections. Then the motor output, because the armature current, the output we get because the armature will be connected to the shaft, no? So and the machinery which we are using will be connected to the shaft. So the power developed in the armature will be more, and that power developed in the armature should overcome some iron and friction losses, and finally we get the shunt torque. This explanation is there in this figure. That's why that time I didn't explain to you. So this is actually a loss torque due to iron and friction losses, and the output machinery we connect to the shaft, and that is a TSH shaft is the torque available. For that we should subtract iron and friction losses from the armature winding, armature torque. So output is 2 pi n TSH by 60. Now we will check out a problem. So we have a 250 volt DC shunt motor which takes 25 ampere from supply mains and having armature resistance of 0.5 ohm and shunt field resistance of 50 ohm. The total burst drop is 5 volt. So 250 volt DC shunt motor which takes 25 ampere from supply mains and having armature resistance of 0.5 ohm and shunt field resistance of 50 ohm. So visualize the figure of a shunt motor and visualize how it will become in the figure. Okay. So now what we need to find out? We need to find out the armature current, input power, mechanical power. All these equations already I have explained. Just see the problem, you will understand more. Output power, if stray loss is 70 watt, then find the output power, then overall efficiency. So just see the problem. So I will be happy if you can pause the video and try the problem by yourself. And if you're not able to understand, then see the solution. Okay. So here we have the shunt motor, DC shunt motor, and we have the input supply which is 250 volt and everything is there. Line current is there, armature current is there, the shunt current is there. And we know the basic equation, IL is equal to IA plus ISH. So 250 is equal to IA plus V by RSH, and we know V by R voltage will be same everywhere because it's a shunt connection. So it will be IA plus 250 by 50. So we get IA is equal to 20 ampere, which is the armature current. And we, from the power equation, I told you like input power is equal to V into I, which is equal to 250 into 25. IL is also given as 25 and input power is 250. So we find that answer. Then the mechanical power is asked. So mechanical power, I told you, we have its electrical equivalent, which is back EMF into armature current. So we have from here EB is equal to V minus IARA. So all these things it's already given. So we found out V minus IARA. Then P is equal to EB into IARA. So 235 into 20 is 4.7, 4,700 watts. That's PM. And we know if straight, because the power available in the PM is not the actual power. We need to subtract the stray losses from there, and stray losses given us 700 watts. So the output power will be equal to 4,700 minus 700, and that's the 4,000 watt. And overall efficiency will be output by input. So it will be 4,000 by 6250, and that is 64%. Understood? Okay. So now we have the your second question here. This actually I want you people to solve because I want actually I have solved it there, but I want you people to solve in today's class. And the next class I will give you the solution. So it's a shunt motor, compound shunt motor. So if the diagram you know, then these are the inputs given. So we should calculate the P input, IA, ISH, PM, copper loss. Same question, just it's a shunt compound motor. Okay. Okay. Thank you.